Here we're going to be talking about static equilibrium. Basically, what static equilibrium means is that a particle is not moving. It's not going anywhere. It doesn't have any acceleration, right? In order for this to be true, if it's not moving this way in the x direction or it's not moving in the y direction, another form of movement could be moment, or torque. So it can be like this. Imagine like this type of rotation. We call it moment in engineering. Okay, so basically it doesn't have any of these movements. It doesn't move, aka no translational movement or rotational movement. It doesn't have any of the above. In order for this to be true, we can look at this equation, F equals ma, right? And then we can come up with the following equations, which is sum of the forces in the x direction must be equal to 0. That's number one. Our second equation is sum of the forces in the y direction must be equal to 0. And our third is sum of the moments about any point, or about the point, I should say, should also be equal to 0. In order for there not to be any movement in order for our object to be in static equilibrium, all of these conditions must be met. So this is pretty much our parameters for solving problems in statics when dealing with static equilibrium. Okay, let's look at our first example for a very simple particle equilibrium problem. So let's say that the chandelier is 5 kilograms, has a mass of 5 kilograms. Then let's try to find out the forces acting on this chandelier, and the force acting on this particle, aka in this case the chandelier, will be our particle, right? So knowing that, we have to understand first that kg is not a measurement of force, it's a measurement of mass, right? So in order to turn it into mass, we need to in order to turn it into force, we need to turn the 5 kg into a force, right? So force would equal our mass times acceleration. In this case, 5 kg times the 9.81 meters per second squared, meters per second squared, will give us approximately, let's say for the sake of this example, let's say 50 newtons, which is just I'm just rounding up a little bit. In reality, it would be like 49 newtons, but let's just say for the sake of this example, 50 newtons from the chandelier. Right, so that's our force from the chandelier due to gravity, aka our weight. We can also call it our weight, 50 newtons. Now let's draw a little free body diagram. This right here will be our chandelier. This right here is a chandelier. We can even simplify it more and just represent it with an actual particle, like a little dot like this. This represents our chandelier, and now we're gonna add the force, our external force from the gravity of the earth. This right here is our weight, right? This is going down because it's pulling down to the earth. Imagine this is the floor right here, the earth, and we have our weight acting down on it, going towards the earth. So that's why this weight right here is this right here, right? Just want to make it clear. And then right here, 50 newtons. And then we have a force here, an equal and opposite force from the chain acting on our particle, right? This force is provided by this right here, this little chain. That's what it is. That's our other external force acting on our particle. When we try to look at these problems, we try to find the external forces acting on the particle. In this case, we got the external force of gravity acting on the particle, right? 50 newtons, the weight. And also we have our chain resisting that gravity, which is our other external force acting on our particle. So now our problem is finding out this reaction from the weight of the chandelier acting on our chain. So we call it W. We can call it F of C, right? F of C, force from the chandelier due to gravity. And we can call it our tension. Actually, let's call it force of rope. This is supposed to say rope. Okay, force of rope. So now if we go back to our equations, now we have our free body diagram with our free body and all of the forces in the y direction, x direction. There's no forces in this case. And also there's no moments acting on this particle in this case. So we go back to our equations and we do our sum of the moments in the y direction, because this is all the forces that we have in this case. They're all acting in the y direction. We can write our equation. So FR going up from our rope, we can just assume it's going up, right? Assume it's going up. FR. Let me make this neater. FR going up. FR. And then we have to add our forces from the chandelier, which is going down due to gravity, right? Down, FC. And then we can simplify this more by adding, assuming our convention up is positive and down is negative, then we can assume, okay, FR plus because it's going up, so FR, force of R, aka the rope. And then since we have an arrow going down, we can just call it negative here. So plus a negative is just a negative, right? Minus F of chandelier equals, remember, 0. Some of the forces in the y direction needs to equal 0. So we just call it 0. In the y direction, 0. So furthermore, if we simplify our equation, we can see that FR equals F of FC, right? So what does this mean? It means that force of the rope is going to equal force of the chandelier. And since we know that our force of chandelier is 50 newtons, we can just plug it in. F of C, 50 newtons, equals force of rope, which is 50 newtons. So force of the rope equals 50 newtons. So if we go back to our free body diagram, we can see that this makes sense, because force of the rope, which is this one, FR, is going to equal 50 newtons. And it's equal and opposite to the force of the chandelier due to gravity, which is 50 newtons. So it makes sense, right? We'll continue right now with another example. Okay, let's go over another problem right here, our second problem. So the problem reads like this. A force P is being applied to a 100-pound block resisting on the frictionless incline as shown. Determine the magnitude and direction of force P and the contact force on the bottom of the block. Okay, so we have this block and it's being acted on by this force P. Again, this is a statics problem. And so we're trying to find the magnitude of P and the direction of P. In this case, the direction of P is already given, which is 10 degrees right here. So in reality, we're just looking for the magnitude of the force P. So let's start by drawing our free body diagram. So this is our point, our center of mass of the block, and we're going to translate it here. We're going to put a little block here. That's our free body diagram for the block. This right here, the one I just drew, the little circle, it represents the center of mass. of the block, which is where all the forces are being applied in this case. Okay, let's do this. Let me write it down a little bit lower. Here, right here, center of mass, P. Okay, so we have our little center of mass here, and we know that there's a force P being applied here at 10 degrees, right? Right here, 10 degrees. This is our force P. Let's do this, hold on. I'm gonna move this here. So that's our first force. Our center P is being applied at 10 degrees right there. You see, all we're doing is moving this force from here, this force right here, P. We're just translating it here. We're translating this force P, we're putting it here. What other forces do we have acting on our system? Let's see. So we have our weight, which is going straight down. Always it's going straight down. Actually, let's start with our normal force. We have a normal force here, which is perpendicular to our surface. This is called a normal force. So the normal force is always, by definition, perpendicular to our plane, to our floor in this case, or to our surface. So we have our force perpendicular, a perpendicular force, which is called our normal force. Okay. Now we're gonna make our little diagram here for our normal force. So imagine we have our block here, and it's being applied like this, in this direction, right? And so imagine we have this. So this is normal. And then if we add the other 25 degrees, what's this angle gonna give us? Pretty much 115 degrees. So we know that this normal force is acting on our center of mass at 115 degrees, right there. This right here is 115 degrees. Normal, we're gonna call it normal force N. Okay. And finally, we have the weight of the block, which is this force right here, the weight of the block. So we're gonna put it here, weight of the block. And that one is just acting straight down because the gravity acts straight down on the floor. And we're just gonna put it here, which is equal to the weight of the block. Remember, the weight equals, it's a unit of force. So a force equals, weight represents the force, which is 100 pounds, 100-pound force. Okay, so that's our three components acting on our three force components acting on our block. Just to recap, we have P here, this external force P right there. We have N, which is the normal force acting on this, the normal force acting perpendicular to the surface. That's represented in this diagram right here. And finally, we have the weight, which is represented by this right here, just going straight down. Okay, so from this, we can start writing our equations. Remember, the sum of the forces in the x direction and the y direction needs to equal 0. Sum of the forces in the x direction need to equal 0. In this case, there's no moment. There's no moment being applied to this, so we don't have to worry about this one for now. The moment, some of the moments, but it still equals 0. But we don't have to worry about it because we don't have any moments acting on this. So let's begin. So we can start by adding up the y component of P. This is gonna equal, if we do, we can do a sine of 10 degrees, sine of 10 10 degrees times P, which is our force, P. This is the y component of this vector right here. So we have our vector, and we have our y component and our x component. That's basically what I'm doing here, P sine 10 degrees. That's the y component of the force P, and then we're gonna add n, same idea, sine of 115 degrees. And then we're gonna add our weight, we're gonna add our 100-pound weight acting down. So it's gonna be a negative since it's acting in a downward direction, right? So we're gonna do minus 100-pound force. I'm just gonna write pounds because I'm just gonna write pounds in this case, but technically it's pound force. Or actually, the problem doesn't say pound force, so we could just leave it at pounds, because we can just keep our units the same, and in this case talk about pounds without having to use force units. So we can just say pounds. And now let's solve for the x direction. So some of the force in the x direction, we're going to do the same. We're trying to find the x component of this. So how do we find the x component? P cosine 10 degrees plus, now we find the x component of the n cosine, which is this one right here. So we have our little arrow pointing this way, and we're trying to find the x component and the y component, and that's going to equal. So from our little n force right here, we're trying to find the x component and the y component. So right now we're doing n cosine of 115, and then there's no x forces acting in this diagram right here. We don't have any x forces, any force in the x direction, so plus 0. And all of this again equals 0. And what we have here is basically a system of 2 equations and 2 unknowns. So you guys can just plug it into a calculator or figure it out. I'm not going to go over this in this video because I don't think it's relevant to this. I mean, it's kind of relevant, but if you guys can't solve a system of 2 equations, then you guys should probably review that in like algebra and stuff. So basically, we solve for these, and you guys can check your math. I solved the equation. Basically, P, after you solve your system of 2 equations, 2 unknowns, the P equals 43.8 pounds, and the N equals 102 pounds. We have to remember that when talking about forces, we have to talk about magnitude, which is the pounds that we described here, but also direction. So we have to also describe the direction of the vector. In this case, P, as we established here, we set it equal to 10 degrees because that was given in the problem, 10 degrees, right? And that's how we did our math, based on using the 10 degree. So we know that this right here is at an angle of 10 degrees. So we can just write it something like this. At an angle of 10 degrees. This looks like 100, so I'm going to erase it. But basically, all I'm saying is that it's at that 10 degrees. 10 degrees. And this one as well, we know that it was normal to the surface, which was 25 degrees. So 25 plus 90, as we can see here, is going to give us 115 degrees. So we can just say here, 115 degrees. And that's how you solve that problem. Let me know if you guys have any questions in the comments. I'll try to make better videos as I practice more of these. Thank you. Just to summarize what we did here, we found the force P, right? We found it to be equal to 43.8 pounds. And also we found the magnitude and direction of the force P, well, we already talked about that. And then the contact force on the bottom of the block, which is right here, N. So we found both magnitude and direction of N. And also we found the magnitude of P. So basically these are the forces acting on the block in the state of equilibrium, which is what we were talking about in this video, which is static equilibrium. So when you have this force, 100 pounds acting on the block because of gravity, because we're on Earth, these are the reactions that are corresponding to this 100-pound block. We have the reaction of N, and then this external force P. So that's basically what the problem was asking us to do, and that's what we solved for in this problem. This is just a little summary of what we did here. And just to summarize the video, basically that's what we're doing in statics, trying to find the trying to solve problems with the understanding that the sum of the force in the x direction, y direction, and moments equals 0. And we use these equations for all of our statics problems, basically, which means that the problem isn't moving. I'm sorry, not the problem. The particle is not moving. It's in static equilibrium. That's basically what this means. Hope you guys enjoyed the video. Thank you.